In this video, we are covering Lesson 2 from the second part of Unit 4, and within this video, we're going to focus on transformations of parent functions. We'll actually spend another video talking about specific parent functions, but for this one, we're going to be talking about what we call transformations. Now, we've already talked about transformations in a sense already. If we go back and look at our notes from the last video, the vertex form of our quadratic equation is indeed a transformed function of x squared. This h and k value simply shifted what we would call a parent function, our x squared graph. It shifts it to the left or to the right and up or down. And it also stretches the parabola taller or shorter, perhaps even wider or narrower. And all of those transformations are accounted for with these three parameters. Now, in actuality, there are four parameters that we're going to consider. And I'm going to identify them as h, k, a, and b. And as you'll see, the h, k, a, and b values will all perform individual transformations to a parent function. But also it's worth noting that we can combine those. Any a, b, h, and k value combined will perform multiple transformations simultaneously. Now, shifts, which are also called translations, you may have heard that in geometry class, shifts are accomplished by either adding or subtracting values on the inside or outside of a grouping symbol. So you'll notice that in both examples of this shift transformation that we have a plus sign written next to the letter h and next to the letter k, but it could just as easily be a minus sign as well. So sometimes you'll see this symbol here, plus or minus. If you take a look at the stretches, by comparison, in order to stretch a graph, we have to multiply by the parameter. So adding and subtracting, that shifts our graph. Now you'll notice that a horizontal shift, a parent function will be shifted horizontally, that means left or right, by adding or subtracting a value on the interior of a grouping symbol. And I'll explain more about that in just a second. Vertical movements are completed again by adding or subtracting a parameter value, but you'll notice that that addition is performed on the exterior of our grouping symbol. If we were to take our parent function from the last lesson, f of x equals x squared, we recognize, or should recognize, that this is a parabola centered at the origin, and it looks something like this U shape. If I were to apply a shift to this, or if I wanted to apply a shift to this graph, I might write something like this: f of x minus 2, which therefore would look like x minus 2 squared. And by knowing what the parent function was, x squared, and applying this transformation, I would recognize immediately that this equation generates the exact same graph, simply shifted to the right 2 units. And yes, a subtraction means a shift to the right, whereas an addition would mean a shift to the left. More on that later. If I were to take the function and add 2 to it on the outside, say x squared plus 2, or without the parentheses, that would be fine. We could call this x squared plus 2. We again would have the same shape as the parent function, only shifted up 2 units on the y-axis. If we were to combine both, say f of x minus 2 plus 2 on the exterior, and have a somewhat complicated looking equation like this, x minus 2 squared plus 2, well, that's going to account for both a horizontal shift and a vertical shift simultaneously, and our parabola would have been shifted to the right 2 units as well as up 2 units, and now would be located here in this position. Often it's easier to graph a transformation by simply transforming a parent function, and we often will investigate other functions in terms of transformations as well to help answer questions about a particular scenario. Now, if I were to stretch this graph, if I were to make it taller than usual or shorter than usual, that would require a vertical stretch. We will stretch the graph taller or shorter. Let me see if I can illustrate that here. If I had a parabola and I were to stretch it taller, whoop, that did a combination of movements here. There we go. Stretching it taller would require an A value. Stretching it shorter would require an A value. This is what we would mean by a vertical stretch, changing its orientation in this direction. A horizontal stretch would be more like this, where we're making it wider or narrower. And of course, we can apply both sorts of stretches simultaneously, and that would make the graph change in size. At first glance, a horizontal and vertical stretch could both be accomplished by one or the other parameter. For example, I could make a graph appear wider by simply reducing its height vertically. I can make a graph appear taller by reducing its width horizontally. But there will be times where recognizing the difference between the two will be more helpful. Now, in a similar fashion as before, you'll notice that the horizontal changes, the horizontal shift and the horizontal stretch, both occur with values that are being applied to the interior of a grouping symbol. The H value for the horizontal shift and the B value for the horizontal stretch occur on the interior of our grouping symbols. For our vertical changes, if we were to stretch vertically or shift vertically, well, those two changes have occurred on the exterior of our grouping symbol. And that's a pattern that you certainly can memorize and utilize in the future. Horizontal changes occur on the interior of our grouping symbol, vertical changes occur on the exterior. You may also notice that stretches, as I said before, are accounted for by adding or subtracting our parameter values, whereas stretches occur with multiplication of parameter values, and that will be true in all cases as well. Now, a byproduct of our stretching is what we call a flip, and we can actually change the direction of a graph by flipping it vertically or horizontally. And in keeping in line with the patterns that we started to establish before, a horizontal flip, if we were to flip horizontally, that's going to be accounted for by a change on the inside of our grouping symbol. And a vertical flip would be accounted for by a change on the exterior of our grouping symbol. And the changes that we're referring to here are simply using the negative symbol in front of our variables. And so I don't know if it's worth it to you to create a flashcard or just to rewrite this chart and pay close attention to the patterns that we've just established, but the quicker you can memorize these patterns, the quicker you're going to be able to apply them, and more thorough understanding of the behavior will be learned. After we learn this behavior in an abstract sense, we'll start to see the applications of that in later assignments. Now again, all of these parameters, A, B, H, and K, along with the plus and minus signs for A and B, they will be combined to create several different changes or transformations to a single function. The added benefit to understanding about these translations is that we may not, or we don't necessarily need to know what the original function is. If we had a picture to work with or a general shape of the graph, we would know how it would be modified and then interpreted by simply looking at the transformations that follow. For example, the function f of x. I don't know what the equation is for f of x, but evidently the function f of x produces this shape. It's kind of this angular design here. Now, if f of x is the original shape and we apply a transformation in this order to it, we should be able to determine what the new shape would be. And hopefully you recognize that we are subtracting a value, so this is going to be some sort of shift. And since we're subtracting on the outside, this is on the outside of our grouping symbol, then this means that it's a downward shift, and we're going down 2 units. So what I need to do is I need to take this picture and simply shift it down 2 units. So I can cheat just a little bit since I have electronic ink here. I'm going to copy this, and you can redraw this carefully on your paper, of course. I'm going to copy this. I'm going to bring it over to here. So there's the original function, and if I needed to shift it down 2 units, then I'll just shift it down 2 units, and this is the resulting shape. Now this graph is represented by f of x minus 2, and oftentimes we'll write y equals f of x minus 2. Oftentimes when students complete this work on paper, what I see them do, and I think this is a good technique, is they'll draw the original picture with a very light, a very faint dotted line, and then they'll draw the new picture with its transformations with a slightly darker line. Kind of like I've done here. The black ink is going to represent the new graph. In fact, I'll choose a different color to make this stand out. I'll choose a light blue to make this stand out here. So this blue graph represents the final answer, the result after transformation, and this dotted gray line, that represents what we had started with. So maybe I'll do the same over here. This is a sketch of the original function, and in question B, we're being asked to graph this guy here. Now, we have another addition or subtraction, so we know that this is a shift. And this shift is occurring based on the change that's on the inside of our grouping symbol. And when we shift due to a number that's on the inside, we're shifting because of the addition or subtraction. And we know that it's on the inside. So this is going to move our graph left or right. But what you have to be careful of is that when we apply changes to the interior of a grouping symbol, we must think the opposite of what that symbol might imply. And a subtraction here actually means a rightward shift, not a leftward, but a right shift of 2 units. So we're going to shift this graph right 2 units. So we're again picturing where the original graph was. This was f of x, this dotted line here. And if I were to shift that to the right 2 units, I might think of it this way. I might just start with some key data points. This spot needs to get shifted to the right 2 units. That's going to put it right here. This spot has to get shifted to the right 2 units. That's going to put it right here. This spot has to get shifted to the right 2 units. All spots have to be shifted to the right 2 units. And so without the luxury of having electronic ink that you can just drag and move, we instead might think about, again, the key data points and what happens to each one of those as they're shifted to the right. So again, if this spot was shifted to the right 2 units, that would show up here. If this spot was shifted to the right 2, we'd be here. Again, here, here, and here. And all of those data points should be connected with a line in order to recreate the graph. And if you had a ruler, that would be very nice to use right now. And this graph represents the transformation that we expected to see, a rightward shift of 2 units. And this is represented by the equation f of x minus 2. Using your notes and the examples so far, can you complete C and D on your own? You'll notice that we have a negative symbol on the outside of the grouping and then again on the inside of the grouping symbol in these 2 examples. So what will those graphs look like? Please pause the video now and resume playback in a moment to check your work. And here are the results for C and D. In part C, we encountered a vertical flip because the negative symbol was on the outside of our grouping symbol. And so what I imagined here was the result of each of these data points, say this position here being flipped over the x-axis. So if I were to flip that over the x-axis, pretend that that's a mirror here, then it shows up down in this position below. If I were to do the same with other key data points, you can see where they would align. And so from a visual perspective, I think the flip tends to make sense. What also might make sense is if you think about the coordinates. Now, the coordinate of this first position was -2, 2. And if we put a negative sign in front of the grouping symbol or outside of the grouping symbol, this is effectively changing our y-axis, or our y-coordinate, I should say. The x-coordinate remains the same, but the y-coordinate gets flipped. Instead of a positive 2, it becomes a negative 2. And now that coordinate has been identified. You could do the same for each coordinate along the way. Now, as far as a solution to the question goes, I'm really only interested in the end result. If you leave evidence of your original function here, that's fine. Just make sure that it's very light and not the focus of our attention. For part D, we required a horizontal flip, and I performed the tasks much the same way. I considered the position of this original point, and I flipped it over the y-axis, and it ended up here, 2 units to the right of the y-axis. So again, I'm imagining this mirror flipping the graph right across the y-axis. Did that for this data point. This data point flipped and stayed where it was because there was no other horizontal position for it to fall. And then this data point was flipped horizontally across the y-axis and landed here. Again, the solution or the answer to this question is this darker or heavier blue line, not the dotted line to begin with, but that was just used for reference. Now, question E, the instructions say to graph y equals 2 f of x. And with the 2 on the exterior being multiplied by f of x, that's going to be a stretch. And because it is on the exterior, we're going to call this a vertical stretch. And so I would say something like this, that it's a vertical stretch of a factor of 2. And so in this case, a factor of 2 being on the outside, it behaves much like we would normally expect, and it's going to make the graph appear taller. And when it comes to stretches, let me first recreate the original picture. There's our original picture. If I were to stretch this twice as tall, effectively what would be done is this right here. Well, how do we account for that? How do we accomplish that? How do I verify that all of these coordinates land where they're supposed to? Well, what I would recommend is, again, thinking about the coordinates in the y position associated with them. This first coordinate here is at the position -2, 2. And if I stretch this twice as tall, our 2 in the y-axis becomes twice as tall, and it now shows up as 4. We end up with a data point up here. This data point here is again a 2 on the y-axis, and when we stretch that twice as tall, it appears here. This data point had a y value of 2. This data point had a y value of 1. The y value of 1 here, when doubled in size, appears there. This y value of 0, when doubled in size, remains 0. We're not changing the x values at all because there is no horizontal component to this transformation. We simply have a vertical stretch on account of the a value that's sitting on the exterior. If I were to connect these points with a line, then the resulting graph would look something like this. When completing part F, we see another stretch, but this time our factor is on the interior, and our parameter is on the interior, this 2 here. But since this is on the interior, we need to think the opposite of what we would expect. Instead of making the graph twice as wide, this actually makes it half as wide. That's the behavior of these parameters when they exist on the interior of a grouping symbol. And if you haven't done so already, it might be a good idea to note this. Let's see, I'm not sure if you have enough room, but it would be worthwhile to note this in summary. When we apply a change as far as a vertical shift and a horizontal shift or a horizontal stretch, a change on the interior of our grouping symbol, I want you to think the opposite of what you would normally expect. A plus, instead of shifting to the right, means shift to the left. A multiplication of a large number like 2, 3, or 4 doesn't mean stretch, it actually means a shrink in that direction. So back to this example, part F, if our parent function was in this shape, then the transformed function has to be half as wide. Instead of having a x value of -2 here, instead we'll see an x value of -1. That's half of 2. Instead of an x value of 0, well, half of 0 is still 0, so we're going to retain that position. Instead of an x value of 1 right here, we're going to go to half of that. And instead of an x value of 2, we're going to utilize an x value of 1. All y coordinates remain the same for these transformations. The only thing that changed was our x coordinate, because this was a horizontal change or transformation. And here again, the result is this heavier blue line, not the gray dotted line that leads to it. In fact, it would be helpful for me while scoring your work on paper to erase your parent function, especially if you draw it light enough, it'll be easy to do so. If we can erase that parent function so that I can only see your transformed function, that would be helpful for me. For our last two examples, we have the functions rewritten down here, and this is going to create a combination of functions, to say the least, or combination of transformations, I should say. This multiplier is on the exterior of the grouping symbol, so we know that this is a vertical movement, and since it is a multiplication problem, we should recognize that this is a vertical stretch. So we have a vertical stretch, and on the exterior we behave just as we would expect, and this vertical stretch means that this graph is going to end up being half as tall, so the factor of a half here. This plus 2 is on the interior, so that's going to be some sort of horizontal movement, and since it's an addition or subtraction sign, that means it's going to be a shift. So I know that this is a horizontal shift, and because this is a plus 2, I would like to think that this is going to move the graph to the right 2 units, but we have to think opposite in this case, so we're going to shift left 2 units. So if I'm thinking of the parent function, I'm going to use this blue ink just to make my point. If I'm thinking of the parent function, and I should really follow the order of operations when applying these transformations. So the first thing that I'll do is the interior movement first. Any changes that are being done on the interior of the grouping symbol must be accounted for first. And I'm going to shift this graph 2 units to the left. So if I shifted this 2 units to the left, it's going to show up here. And now if I stretch this graph vertically by a factor of 1/2, well, that means that the graph ends up being half as tall. I'm going to stop right here, because again, at this position I'm considering the y coordinates, and if the y coordinates are all chopped in half, the graph becomes half as tall, and we end up with an image that rests right here. And now our end result has been presented. A graph that's been shifted to the left 2 units and has shrunk or stretched by a factor of 1/2. For this very last example, we've got some numbers that are written slightly out of order, but perhaps you'll recognize that instead of 2 minus this function, I could write a negative f of 1/2 x and put the plus 2 at the very end. Because addition is commutative, this is an addition of 2, and I can place that either before or after this other term. And I've chosen to put it at the end because that helps me identify my k value a little bit more easily. So we've got a negative symbol in front of the function, so that means that we're dealing with a vertical flip. We have a b value of 1/2, so that's going to be a horizontal stretch. Now remember, think the opposite, so instead of being half as wide, this ends up being twice as wide as usual. And then this plus 2 on the exterior means that it's a vertical movement, and because of the addition, I know that it is a vertical shift. And one more time, we're going to follow the order of operations, so I'm going to start within the grouping symbol, move to the multiplication sign. This is technically a -1 times this set. So interior of the grouping symbols, move to multiplication, and then addition. So we'll stretch horizontally, we'll flip vertically, and then shift vertically in that order. So if we had the original graph here, the first thing that I would like to do is stretch it by a factor of 2 horizontally. Even though the number was 1/2, we want to make this graph twice as wide. Now my software is kind of helpful, but I do have to be careful here. If I stretch this twice as wide, I still need it to be centered at the center of the graph for the time being. So I went a little bit too wide there. Here we go. Maybe not wide enough. This is where I said, or this is why I said it's going to be a little bit tricky, trying to get everything to line up. Okay, I'm happy with that. This graph has now been stretched twice as wide. We need to flip this over vertically. And I do have that as an option built into this software. So we will flip this vertically. Now, we have to flip across the y-axis. So even though the orientation of this picture has changed, we do need to make sure that it ends up in the right spot. Because again, just a second ago we were sitting up here. And if I were to flip that vertically, that means vertically across the x-axis. All of the y values are inverted. So this point had to end up down here, this one ended up here, and so on. All of these points in between were flipped across the y-axis. So we've now flipped the graph vertically, and that followed our horizontal stretching. Now what we need to do is account for the vertical shift. So this entire graph will be shifted up 2 units. Generally, if I've got the ability to do so, I'm going to look at just one point and imagine where it will end up, and the rest of the components should follow. And now we've ended in this position. Performing multiple transformations can be difficult, especially if we're relying on just this single copy of the original graph. Imagining how it will be stretched and shifted and all those different moves simultaneously can be a bit of a chore, but with a little bit of practice, I'm certain you can handle it. If you don't have access to an electronic inking device like I'm using here, this tablet computer, I highly recommend using a light touch when drawing by hand on paper. The lighter you draw your intermediate steps, the easier it'll be to erase, and then you can show your movement on to the next steps and so on. If you've got any further questions about the work we've completed in this particular video or along the way so far, please feel free to reach out to me and I'll respond as quick as I can. Thanks for watching.